Yeah. I have made you the host.
Okay, fine. Thank you. Okay, let me take some more examples, but of different categories now. So we have done 3 different systems, butane 1-ol, then S8, and then we did one coordinate compound. Now let's do one simple organic, and let's take a biomolecule like glucose. So again, go to the one blank sample there. And then let's try to create a glucose molecule in the cyclic form. Now again, on the left hand side, you can see there's something like groups and rings. On the bottom, there's a ring. And there are some standard rings there. So we can choose cyclohexane. So if I click in this build panel, you can see that it's a cyclohexane. And that too in which form? You know that in cyclohexane chair form. Each atom has axial bond, equatorial bond. But in glucose, one of this atom will be oxygen. So we have to replace this oxygen. Just a sec, let me stop you from annotating. Just a sec. This simple part. Okay. Sorry. So now we have a 6-membered ring. And now let's replace one of the carbon with oxygen. So we can select this oxygen with 2 single bond and select at one of the carbon atom. So now you can see that we have a 6-membered ring. Let me zoom this 6-membered ring with 1 oxygen atom. Sorry, that's no. Look at that. Some mistake has happened, but let's learn from it. So by mistake, I clicked on and there's water molecule. So I'll simply do Control Z. It goes away. So now we have a 6-membered ring with oxygen atom. So in glucose, the carbon which is adjacent to oxygen has a CH2OH group at the equatorial position. So let's put CH2OH group at this position. So we'll select carbon, sp3 carbon. Click at the end of the spoke. Now we have a methyl group, and then put oxygen OH group at one of the end. So now we have CH2OH at the equatorial position on this particular carbon atom. And again in glucose, the remaining carbon has again 1 OH each at the equatorial position. So again select oxygen with 2 single bond and put OH at the equatorial position. So be careful. So OH at the equatorial position. Okay, just to check that if I have made a correct structure, that can be done. Look at that 5th icon. Now this, if I put the cursor there, this shows that this is a molecular formula. So if I click this, you get a molecular formula C6H12O6, and you know that glucose has this molecular formula. Again, if I click at the next icon, this is molecular, this ABC, name structure. If I select this, it is beta D glucopyranose. So that's okay. Let's come out of this build panel. So now we have this glucose in a cyclic glucose. Now we'll do some more chemistry there. Organic chemistry, most of the time they are interested in stereochemistry part there. And this molecule, you know that lots of chiral center there. So this molecule is optically active. So if I want to change this molecule to its anomer. So what is anomer? The anomer has OH, the carbon which is adjacent to this oxygen. If we change the position of this OH from equatorial to axial, it will convert to its counterpart anomer there. So how to do that? Select this particular atom and do right click. A sub menu appears there. Selected, right click sub menu, and then you can see that it's the invert atom chirality. So look at that, something will happen. I'll do it again. Right now the OH is at the equatorial position. If I select this atom, selected, right click and then invert atom chirality. If I click this, look at that, that OH has moved from the equatorial to axial position. Now if I look at the name of the structure, now it is, you can see that it has got converted from beta D-glucopyranose to alpha D-glucopyranose. Fine. Okay, let's do a few more chemistry there. Go to the again, if I have to modify this system, chemical system, what I have to do, I'll go to the, because if I click the first icon, this is new panel there. If I click the second icon, I can modify this particular model there. So if I click this, again, add atom, if I click on this, add atom, the palette again pops up there. Now let's put some water molecule around this glucose, randomly some water molecules. If I keep on clicking, I'll get water molecule around this particular glucose molecule. Let's put 7, 8, 9, 10, any number there. Okay, I'll go back, come out of this build panel. So we have some water molecule. Okay, so one feature I just forgot to mention there. In computational modeling, molecular modeling, lots of people are interested in molecular dynamics. So for dynamics, the two different type of calculus, static calculus and dynamic calculus in there. And dynamic also that can be done in classical molecular dynamics. That's what we do in bromics and charm there, amber there. And then we have some ab initio molecular dynamics there. I'm not going to the theory part. Today we are not going to theory part. Look at the simplicity of this software. You don't need to worry about all those complexities which the computational chemistry do in everyday life. There in their research life, there are lots of keywords and they have to remember all that programming thing. Nothing of that sort in this particular software. You are going to only for the application part, and it's all mouse driven, very easy to understand. But actual chemistry is going in the background, and the mother software is Spartan. We'll see some example from the Spartan also there. So let's do this molecular dynamic. On the bottom, you can see there's a play menu there. If I click on this play menu, look at that. Molecules are moving now. I'll stop again. I'll put it there. I'll zoom in there. And now, again, I'll start this. Now, you can see on the right corner, bottom right corner, there's something 10 power minus 12. What is this 10 power minus 12? This is the time scale in which the molecules are vibrating, moving, and that's in the picosecond. So actual chemistry there, in actual nature there, is happening at the level of picosecond. That's a time scale, picosecond there. Now one more feature I'll show you there. Now you know that in this water molecule and this glucose, there are lots of OH group there. And between the OH group, we have hydrogen bonding. So if I were to see this hydrogen bonding, I'll go to the style, and you can see there's an option called hydrogen bond. So if I style, again I'll go back, style, and then you can see hydrogen bond. If I click on this hydrogen bond, you can see that hydrogen bond between this intermolecular hydrogen bonding between two water molecule, between glucose and water molecule. Now again I start this, you can see something happened there. So water hydrogen bonding, glucose water hydrogen bonding. Let me stop now. Okay, so you can see that you can do lots of things from this software, and it's mainly for the teaching purpose there. I'll tell you that whosoever uses this particular software for their teaching thing, your lecture will go to the next level, because visualizing a structure, visualizing structures altogether gives a different meaning and understanding also there. Okay, I'll take a few more examples. Go to the build panel. We did some entry level, advanced level. I'll take one example from solid and one example from this bio system there, peptide, nucleotide. So I'll click on the solid. Now in solid, we know that we have different types of solid. All ionic compounds are solid, so ionic solid. Lots of metals are solid there, except mercury at room temperature there. All of them are solid. Then we have molecular solid, covalent network solid like diamond, silicon, they are covalent network solid. So let's click to this ionic solid. Within ionic solid, we have different type of ionic solid, AB type, AB2 type, and then spinels there, then the perovskite structure there, different type, means recent flavor in solar cell is perovskite there, perovskite there. Now, the most simplest one is your rock salt structure, sodium chloride structure. All alkali metal halides except cesium chloride, cesium bromide, and cesium iodide, they crystallize in rock salt structures. If I choose this rock salt structure, and if let's change sodium plus to K plus. So if I select K plus in place of chloride, if I choose bromide ion, and then you can replicate also. So if I click this, now we have a potassium bromide crystal, and you are taking the replication is 2:2:2. Along x-axis 2, along y-axis 2, along z-axis 2 there. Now come out of this build panel. I'll show you one very interesting feature. Normally, students are interested in, they want to know the coordination number, total number of closest neighbor there, nearest neighbor there, equidistant nearest neighbor. Now, how to identify in this particular structure there, that can be done. If I click one of the ion, if I click this, look at that, the bottom selecting atoms bromine. So we have selected bromide ion. And if I click right click, I've selected this and then do the right click, sub menu, and there's a very important option called set clipping center. So if I choose this set clipping center, now a sphere is created around this bromide ion. But we can't increase the size of the sphere in this white color. Again, if I click this, the color changes. Now you can increase or decrease the size of the sphere. So if I decrease, we have now simply one bromide ion. And now if I increase, just by help of zoom in that scroll, look at that, 6 potassium ion pops up around the bromide ion and the octahedral form, perfect. Now it's very clear to the student, the coordination number, the total number of equidistant nearest neighbor around this bromide ion is 6. And again, if students are interested to know that next nearest neighbor, so you know that the next nearest neighbor of bromide ion will be bromide ion itself. And how many number? Anyone can guess in their mind how many number in sodium chloride structure? The answer will be 12. Let's do that. If I increase the size, 12 bromide ion, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bromide ion pops up. Go back, 6, 1, then 6, and then 12. So you can play with this. If I have to come out of this, right click, unset clipping center. Let's practice one more time. Now if I select potassium ion, the smaller one, click this, selecting atoms potassium ion, and then right click, set clipping center. Then again, not in this form, you can increase or decrease the size of the sphere. Now again select this, decrease the size. Now simply we have potassium ion. But if I increase the size sphere, look at that, how beautifully this bromide ion appears in the octahedral geometry around this potassium ion. And again, if I increase this, the 12 potassium ion appears. Sure, I'm getting this chat. Can we get this video? Obviously, you'll get this video. You'll get this video to practice. But I assure you that if you play for one day in new users, all those, whatsoever I'm doing, it's all given there. It's very well documented. It's very simple to understand. Go through that one by one in the new user. Once you complete all the tutorial of the new user, you'll have the mastery in this particular software. And you can see that it's really wonderful. I don't know, in the last 15 years in the field of computational chemistry, I have used lots of software, but none of this software is as user-friendly as this particular software there. Fine. Okay, again, unset this clipping center. So we did one example in solid state. Let's do one more because you will be waiting for Professor Ergen himself to come again and come to the next session and take over this level to the next, because from the developer himself you want to hear from him. So I'll take one more example and then I'll end up that. I'll come back again after some time. So we'll do alternate basis there. So one more example from, I'll take this biomolecule because I know that lots of participants are from the bio background. So they will be interested in things like protein, DNA there. And whenever we did and during PG level, we used to study the strier and lineager, and you used to see that fancy those models there. You can create all those models in this particular software. Let's do that. So in this drop-down menu, now let's select the peptide. Now, you know that protein is polymer of amino acid. And now we have this palette. You can see that 20 essential amino acids there. Right now, amino acid is selected. Let's try to create a peptide. So I'll go for a secondary structure alpha helix. And now randomly choose the amino acid. Your choice. You can choose any order there. That's your choice there. I'm randomly choosing different amino acid, 9, 10, random. Look at that, top of that, primary structure is getting created now. The sequence of the amino acid. Now, if I click in the build panel, you can see that that's a protein there. Now from this, it doesn't appear that where is this alpha helix. So what I have to do, first thing, in any computer chemistry, I keep on repeating the first thing any computer chemist do is to optimize the geometry. So that's the rough geometry we have created for the protein. Now we'll change the bond length, bond angle, dihedral angle. We change what the software changes that. It's all documented there. Programming is there in the background. If I click, and there's some methods there. When you do computer chemistry, you'll find that there's lots of methods for geometry optimization. I'm not going to that complexities there. Something happened in the background. All classical physics is there. Some quantum level thing can also happen, but normally for geometry optimization and this. If I click the third option, look at that in the drop-down menu. Something happening there. Bond length, bond angle, dihedral angle is changing there. Since there are large number of atoms, so it will take some time to optimize. So rather than wasting time, you know that this will happen within 1 or 2 minutes. This will finish up, but just let's not waste time there. I abort this. Whatsoever has happened there. Okay, now I want to see the real that alpha helix form. So how to do that? Again, please listen me carefully. How I'm going to do that? I'll go to the style. In the style, you can see there is ribbons, and in ribbon we have this bisecondary structure. If I click this bisecondary structure, now it's obvious. It's alpha helix. One more interesting form. Again, go to the ribbons, and you can click the bi residue. Now it's more fancy there. Every amino acid has a particular color, standard color assigned to them. So that's in the alpha helix form, and we know that this secondary structure is because of intramolecular hydrogen bonding. So if we are interested in knowing where is the intramolecular hydrogen bonding, which is leading to this particular secondary structure, now let's again go to the style. We have this hydrogen bond. If I click this hydrogen bond, you can see that we have intramolecular hydrogen bonding there. Okay. The thing which has been assigned to me by Professor Ergen there, I just forgot one more thing. I'll take one again quick tutorial there. In computational chemistry, you talk about something called simulation box. Let's simulate a box there. I'll go to hurriedly. I'll take 1 or 2 minutes and show you that very interesting thing, simulation box there. Now let's try to simulate air. Now in air, we know that O2 is around 21%, nitrogen is around 78%, and rest 1% are different noble gases and others there, other thing there. So let's have only O2 and N2. So if I select oxygen with a double bond, click on this and click at the other end, now we have O2 molecule. Select nitrogen, sp nitrogen, triple bond. click on this, and at the end, now we have N2 molecules. So right now we have one O2 and one N2. Now we want to put lots of O2, lots of N2 in a box there. How to do that? There are two different ways. Either you can select this view, the third menu view, there is an option called simulation cell. Or you can do it shortcut way, right click, the sub menu, this simulation cell. So if I choose this option simulation cell, on the left hand side, you can see there is something called vacuum, gas, liquid, solid. So if I look for this gas, room temperature 25 degrees centigrade, you can change the temperature, you can see the effect of temperature also, you can see the effect of pressure there. Now let's change the number of molecule. Oxygen right now it is 1, now let's make it 22, nitrogen let's make it 78, and then you can change the replication also, that cell size thing also. Right now, let's take 1:1:1 and then apply. Now you can see that in a simulation box, we have O2 and N2, but they're very tiny. To increase the visibility, the best thing will be go to the style and choose the option space filling. Now there's increase in the size. Now it's very easy to visualize. This blue one is your nitrogen, because color code, I said that nitrogen with a slight blue there, grayish blue you can say, and then this red one, that is oxygen. And let's do something there, some chemistry there. Chemistry board, that's a physics. And now these molecules, you know that they do random motion. So if I click on the start simulation thing there, now they are moving. And when they move, they collide with each other with the wall of the container. Just to see that where the collision is happening, I can again go to the style. Look at that, there's in a style, there's collision particle by particle, particle wall. We can choose this option all. Now you can see that the pops of the sphere around. Blue one with the wall, white one between molecule and molecule. That's a collision. If you want to track the path also, again go to the style, go to the collision, so trails, and in trails we can choose this medium, long, short. Let's choose medium. Now you can see that the path is also, because you know that molecules move in a straight line. That's what Maxwell-Boltzmann theory. They undergo collision. Collision lead to every time the velocity of the molecules are changing. And change in velocity will be change in momentum. Change in momentum will create force, and the force will lead to pressure. A gaseous molecule create pressure because of all this collision. Now the physical chemistry, we do the states of matter. You can ask the student to do some plotting. Now if you look at this, one option, last point, and then I'll hand over the baton to Professor Urban. Plot. If I choose this menu plot, now we can see that this add plot. There are lots of plot you can do plotting thing. One simple thing. Let's do the speed distribution, and now you can see that if I stop this and then again start this, slight variation there happening there. Now we have a Maxwell-Boltzmann distribution curve, and this one assignment you can give to the student, change the temperature and see the effect on the speed distribution. And that's what we study in the states of matter. As we increase the temperature, this flattens up. It becomes more broader one, and that you can see if you change the temperature. So that all those study comparison at different temperature, that you can do it. So let me stop from my side, and still 15 minutes is there. So I'll pass the baton to Professor Urban himself.
Dr. Jagan, please take the control.
Let me increase.
Hello.
Just a sec.
We curated the third link also. If anyhow this link, this meeting close, please keep ready the third link, which is available in the chat window. And also we shared on our WhatsApp group. So if this closes,
So
you can.
Professor Urban as the host. Now, Professor Urban, take the charge now, please.
Dr. Sham, if there is any question answer, if there are any questions for your this thing.
I've shifted the thing to Professor Urban now. We'll have it after Professor Urban thing there.
Okay, no, the participants can still ask you a question or two if they are interested.
Okay, okay. Now they can put it in the chat form. I can go through the chat, and when my turn come back, I'll try to answer it.
Sure.
But most of the thing will be answered by
Sure.
Professor Nagarkar himself.
Sure.
Or, okay, I'll compile the question there.
Okay. Okay.
Okay. I'm sharing now my screen for PowerPoint. Can people hear me? Maybe Yatindra or Dr. Kishore, can you confirm that?
Yes. Professor Nagarkar, I can hear you. Go on, please.
All right. Okay.
It's audible now.
So you got an excellent introduction to the program. I want to provide a little bit of background. The whole idea really of ODYSSEY is to keep everything behind the curtain, you know, as far as the technical issues are concerned. So it's really, it's a hardcore computational chemistry program, but it's all in disguise. There are two computational engines in the program that Dr. Kishore already used, sort of by just clicking on some buttons, namely one for quantum chemistry and another one for molecular dynamics simulation. So around that sits an easy-to-use interface, which you know learned a little bit about how to use that. And then further around that, this is something that he did not touch on yet, is introductory chemistry content. I want to show you a little bit about that. So for that can be used, you know, in lecture, in labs, for computer labs, many different applications. I should do this. I don't want this on. Okay, it's in full screen mode, which makes it a little more difficult. So here is a slide quickly summarizing for the experts among you what are, you know, a few buzzwords about these two computational engines. So there's I don't know why there are now little lines showing up on the, is this on top of the slide? Is that because of me, or anyway? So we have we solve the time-independent Schrödinger equation in the case of the quantum engine, and we simply solve a few hundred-year-old equation, Newton's second law, in the case of molecular dynamics. And you see here in the real world you have to make approximations. They are listed up here. We do a so-called Hartree-Fock calculation for the quantum chemistry with a small basis set, and we use pairwise additive potential functions to solve Newton's equation of motion. Basically, we generate a little movie on the fly. If you hit this dynamics button, as Dr. Kishore did, then you generate frame after frame, sort of on the fly, by using forces that you calculate based on, you know, the structure of the system. You know, how far away are the atoms from each other, and so on. I will close down this screen and do a new share for ODYSSEY. Share this one. Okay, so this is the start page. You all got already or will get an activation code to use the program to play around with it for a while. This would be the start page the very first time you bring up the program that you would see. Let's jump sort of in the most basic form of content that the program includes is simply pre-built models. Quickly go to new users. This is a page that already Dr. Kishore showed you. Here, there's on the left side, you see the examples which explain step by step how you can build all these things. Glucose, for example, he just built. Here, also various solid structures and so on. So you can build all these things from scratch, but you are not obliged to. There's about 1,000 compounds that are pre-built in the program that you see in the stock room, the molecular stock room. So here they are. It's ordered by, you know, the elements at the top for. If I go here for example for carbon, the allotropes of carbon. I mean, a very common topic here is the graphite, the diamond structure, you know, the famous fullerene. Everyone shows a buckyball. Here's actually fullerene as a powder. And always I should bring it on space filling to show this here is the fullerene powder you can buy for, I don't know, a few $100 for a gram. Diamond, if you put it on space filling. Here's the graphite. If I put this on space filling, graphite, I can illustrate by, if I'm holding down the control key of the keyboard, and I'm using otherwise the mouse functions that Dr. Kishore explained. Right button translates, so I can translate here this level. I can translate here this level, and so on. If I put this here a little bit, squeeze it together a little bit, and then start the simulation. If I don't do it too drastically, it will push it back into the gap will close again. If I do something too drastic, eventually it will break apart. You know, you get a numerical catastrophe, and actually it's not. It's a little more robust than I expected. Eventually, it will fall apart simply because you're trying to do something too drastic. You have models of nanotubes. You can look through a model of graphene. Here the dynamics. Always you can, what he didn't show you, it's what's very useful is how far these simulations run depends on how big the system is and then how good or fast your computer is. So if you have a really nice modern machine, things may run too fast actually to see things. So you can, here's the lower left corner, you can slow down the simulations so that you do everything with a smaller time step. The time scale, as he said, it's always 10 to the minus 12 seconds, picoseconds. If you run long enough overnight or so, you can get into the nanosecond regime, but that's sort of about the limit. I'll close this. Here, there's an inorganic section of the stockroom. All kinds of, if I go, for example, here, sodium compounds, here, largely solid structures. Sodium carbonate, here, baking soda. Here, you know, nice illustration here of structure with the polyatomic ions in the solid structure. Here, sodium hydroxide. Sodium hydroxide in solution. So if I take this and put water around it, and it dissociates, and this would be the structure. So this may look like, there's something wrong. Why are the ions so huge? The water molecules are so small. This is because they're shown in different styles. If I put everything on the same style, select all, put it on space filling, oops, space filling. Now everything is shown here in the same manner. Now you see the problem, you can see the ions anymore. Therefore I can select, if I select just the water components, select group, now I select the waters. I should stop that, select the water, select group, and select the waters, and then do the style tube. So now I have sort of de-emphasized the solvent. The big ones here are still the OH minus, but the H2Os are only shown in the tube style now. And so on, a model of borax, amazingly complex, often used, you know, though in experiments in the wet lab. The organic section of the stock group, the same thing you can imagine here. Carboxylic acids, the panel, carboxylic acids, aliphatic. So here I have a model of formic acid, molecule of formic acid, acetic acid. This is immediately shown with a pre-calculated polarity map. And earlier, Dr. Kishore had shown you how you can do it from scratch. This is a pre-calculated one, which is simply stored in the stockroom. It's also bisected, so you can see, sort of allows you, to see the structure inside. If you want to do this from scratch, it's simply, I'll do this here from scratch again for acetic acid. You see how simple that is. A carbon group, I can do it atom by atom. I can also here a carboxylic acid group. I can add to that. Then I minimize the energy quickly, close this, and then I select the polarity map. And here's the thing now calculated from scratch. And here's the calculated from as it was stored in the stockroom. This quantum chemistry here in the stored polarity maps for the stored wave functions of higher quality than the ones you do on the fly. Because think about it, I just hit the button, 3 seconds later or so, you know, the result popped up. I mean, we calculate the wave function from scratch, the square and the electrostatic potential map, and obtained, you know, it all happened within 3 seconds. So you can't, it takes long, you know, to calculate a high quality map takes longer. You can do that with the other program, Spartan, we'll get to in a little while. And I'll leave it at that. Here's also a section for mixtures in the stockroom. I'll skip that. Rather, we'll go to the home page. There's always the participant panel of the Zoom on top of things.
Jargan, just a minute. This meeting will end in another 2 minutes. I have already shared the third meeting link, so we will all join with that.
Okay. Okay. It's yeah. So I have two. Okay. No, I see the remaining time. I have 2 minutes left.
That third link is pasted in the chat.
Please copy the link, Dr. Jagan, you also.
Yeah, I did that earlier. I think I already have it in the. I already have it in the. I already have it. I copied it earlier into my web browser. I think I should be fine. So.
I think we should move to the third meeting now.
Okay, then let's just so it's too let's
let this meeting stop by itself and then we will start.
Okay.
Yeah. Let this meeting close by itself and then we'll start this meeting.
Yeah. Escape.
So please, all the participants, I feel you have copied the third link. Please keep ready. Once the meeting is closed, you just click on the third link and we are diverted to that link only. Okay. We are extremely sorry. We are playing very hardly with this Zoom. So please cooperate and thanks for your patience.
All right. That's I will simply quit Zoom because
Dr. Jargan, don't quit. Just wait for this meeting to end and then I'll start the third meeting immediately.
Okay. Okay. I'll do that.
Yatin, paste that link in the WhatsApp group also, whatever you have created.
Yes. So we have done it. We have done that.
Because lots of messages coming up that they haven't got the link there.
They are following. Yeah, they are following very well. They are doing. So we are copying everywhere.
Okay. And regarding the software also, there are lots of queries. So participants, please contact Yatinder for the software stuff, information regarding software. Mr. Yatinder, you can contact him. His number is with you. So after the webinar, you can contact him for all the details of the software. Don't worry about that.
And I'm taking all the queries in my note. So we'll revert back.
Okay.